Okay, let's quickly run through some more details on the supply chains which are in transition, the various technologies, materials, infrastructure needed to be enabled or established, implemented, whatever word you want to use. So I'm going to just randomly pick some from each chapter. Obviously, my subjective selection. If you want, you will have to go and read or scan through the report, which is very comprehensive in fact. So key elements for each step in selected clean energy and technology supply chains. This is a supply chain that's already in transition. So low emission electricity, there is resource production, material production, manufacturing components, technology manufacturing and installation, operation and infrastructure. So you go from resource production like silica, various iron ore, copper, bauxite, limestone, oil and gas, and you have material productions ranging from polysilicon, copper, aluminum, steel, concrete, carbon fiber, and then manufacturing components like wafers, cells, PV modules to electricity grid, permanent magnets, nacelles, towers, blades, etc. for wind turbines to build wind plants and add to the energy grid. And for low emission hydrogen, you have resource production from nickel, zirconium, platinum, titanium, copper, iron, and so on, to material productions from ore to materials like nickel, zirconium, iridium, platinum, titanium, etc. Manufacturing components like anodes, cathodes, membrane, bipolar plates, CO2 compressor for heat exchanger pumps, etc. if it involves heat pumps, and carbon capture and storage, or electrolyzer to hydrogen plants, and so on. So obviously these are somewhat obvious, and yet each step is critical in terms of supply chain transition and where vulnerabilities could come from and where the risks are, etc. Looking at low emission synthetic hydrocarbon fuels, similarly you have various resource production, material production, manufacturing, technology manufacturing, installation, operation, and infrastructure. I won't read everything, but you are talking about bioenergy and carbon capture with CO2 transport, direct air capture with CO2 transport. You have fuel technology synthesis, so synthesis plants, and hydrogen transport. For battery electric vehicles, again, you have lithium ore, nickel ore, cobalt ore, and copper ore. You have to produce graphite, silicon, lithium, nickel sulfate, cobalt sulfate, copper, and manganese sulfates to build anodes and cathodes to build a battery cell and then feed to the electric vehicle. So you can see the various components of bringing them together. In terms of the renewables and nuclear displacing most fossil fuel use in the net zero energy transition scenarios, share of the fossil fuels has to be plunging by 80% in 2021 to less than 20% in 2050. So here we are going from the historic period 2010 onwards to 2021, and so future here is scenario. So we are talking about coal, oil, natural gas, nuclear, renewables, and others. So obviously by the time you hit 2050, renewables have to do most of the work with some contribution from nuclear, but you'll still have natural gas, oil, and coal. Sadly, coal will still be around in this net zero emission scenario, which basically means irreducible emissions are going to be taken out by carbon capture and sequestration to reach net zero. Total primary energy supply, electrification rates, and energy intensity in 2030 in the announced pledge scenarios and net zero emission scenarios. You're looking at total primary energy supply. Here also we were looking at exajoules, and again exajoules here. So you can look at coal, oil, nuclear, natural gas, renewables, and others for 2021 and 2030, where the announced pledge scenarios are and what's the gap to actually stay on track for net zero emissions by 2050. So here we are at about a gap of something like 5%, which is not bad, and that can be split into electrification and energy intensity as well. And you can see that electrification has to go up quite a bit compared to the announced pledge scenarios, and energy intensity has to drop by about 9% from the announced pledge scenarios to net zero emissions by 2030. Okay. Global mass-based resource flows into energy systems in the net zero emission scenario 2050. You have again coal, oil, natural gas, bioenergy, steel, cement, aluminum, nickel, neodymium, lithium, copper, and cobalt. So when we go into the future, these things are essentially technological promises which have to materialize. So for example, bioenergy, we'll see where we are in terms of pledge scenarios and where we need to go in terms of net zero emissions. So these will be feeding into buildings, industry, electricity generation, transport, hydrogen production, agriculture and other, and energy infrastructure. So you can see that bioenergy is expected to do a lot of work. And of course cement and steel, aluminum, etc. will be feeding these as well. Coal is still there feeding electricity generation and slightly industries. Oil is still there feeding everybody, and so on. So net zero emission scenario by IEA doesn't completely remove coal for the future. It still keeps a bit of it, but relies on technological promise of bioenergy with carbon capture and direct air capture and so on. Total global material demand by type in the net zero emission scenarios. Critical materials here in terms of copper, lithium, nickel, cobalt, and neodymium. 2021, 2030, and 2050. Obviously, copper is a huge part of it, but lithium and nickel. As I said, we will look at the MIT report in another podcast to say that the materials themselves are technically available, but supply chains and other geopolitics will have to be dealt with, and international cooperation between producers and consumers and so on. Bulk materials like steel, cement, and aluminum. Here again, cement still continues to be big, even though it drops here in terms of million tons per year. This is also million tons per year, but the steel amount required remains flat. Aluminum remains flat. Only cement varies, goes up in 2030 and comes down. But again, these are projections, so various assumptions go into making these projections. So you have to look. I have separate podcasts on net zero emission scenarios by IEA that you can look up. Estimated global bulk material demand by end use in the net zero emission scenarios. This is indexed against 2021. So here is cement, steel, and aluminum. So you can see these going. Where do they go? Where are the demands coming from? Come from buildings, transport, industry, electricity generation, hydrogen production, and energy infrastructure. Again, the best way to think about it is to say we have enough resources to transition to net zero emission scenarios, depending on fulfilling the technological promises on which we are depending to produce these scenarios. Global critical material demand by end use in net zero emission scenarios here. Lithium, copper, nickel, cobalt, and neodymium going from 2021 to 2030 and 2050. And we are looking at critical material demand by solar PV, wind, other low carbon generation, EV batteries, EV motor, grid storage battery, electricity networks, hydrogen, and so on. So other is quite big here as well. So you can see that we need to, the demand for critical material will go up significantly in terms of comparing to 2021. You can see that this is orders of magnitude increase. So demand for critical materials increases rapidly in the net zero emission scenario, driven by mainly by clean energy technologies and infrastructure. And I have a podcast as well looking at the emissions from the transitions themselves, and the idea there was that quicker the transition, faster we will get past these embedded emissions in the transitions themselves. In terms of decomposing the change in global direct CO2 emissions from mining selected minerals between 2021 and 2050 in the net zero emission scenarios, looking at million tons CO2, 2021 emissions, activity, ore grade, recycling, and then coming down to efficiency gains, and then electrification and other fuel shifts. So we have to come down here by 2050 to net zero. So these are emissions from mining of iron ore, bauxite, copper, cobalt, nickel, and lithium included here. Electrification as well as recycling and efficiency gains eliminates almost all mining emissions by 2050 in the projected net zero emission scenario, despite rising demand and falling ore quality. Okay, so remember that. So huge dependence on technological promises here implicit in these projections. For large-scale site-tailored technologies, the average lead time between the first feasibility studies and plant commissioning is up to 5 years. So keeping that in mind, current global capacity, announced capacity additions, capacity shortfall in 2030 relative to the net zero emission scenario, and installation lead times for selected large-scale site-tailored clean energy technologies. Here we are looking at years and share of supply in 2030 for the net zero emissions. Gas, so this is carbon capture and sequestration H2, so this is 2021 in green and 2030 in orange, and gap between planned capacity and net zero. So 2030 planned capacity additions in green, average lead time and typical range is shown here. Basic idea is that for DAC the planned capacity additions are here, but in terms of what is needed, there are plenty of gaps between planned capacity and net zero emissions in BECCS, in gas CCS H2, and synthesis. Okay, so this actually is estimated differently by different entities, so you have to be careful whether DAC is really on track by 2030 for net zero emissions. Okay, announced global cumulative investment in mass manufacturing of selected clean energy technologies by region, country, and that required to meet demand in 2030 in the net zero emission scenario. So obviously what is announced and what is required, there are huge differences. So EV batteries have contribute 69% of the gap in the required investment compared to what's announced, and then you have others adding like wind, solar, fuel cells, and so on and so forth. Okay, this is going to be a constant battle in terms of what countries are seeing as necessary and announcing investments versus what actually is needed by meeting the net zero emission scenarios. Direct air capture capacity by country and region for use and storage according to announced projects and what is needed for net zero emissions. So you can see that million tons of CO2 per year, China, other Asia Pacific countries, Europe, North America, Middle East, and so on. So you can see CO2 utilization and CO2 storage, announced CO2 utilization and what is needed. So there is plenty of gap. Announced CO2 storage and what is needed here, there is unspecified in terms of where this will come from. So announced DAC technology deployment is roughly in line with the net zero emission scenario projections for 2030, though stronger policy support is needed to ensure projects proceed. So even though there are pledged scenarios and announced deployments, the fact that is the matter is that they have to be implemented by 2030 and not just sit there as pledges. Capacity of bioengineering with CO2 captured for use and storage by country region. So again, lots of differences between what is announced and in CO2 utilization and storage, and what is needed. So you can see massive gaps in CO2 storage. Many countries are still mapping the potential sites, so announced BECCS capacity amounts to only 1/3 of the net zero emission scenario requirements in 2030. So the fact that it has to work and scale up is different from the fact that even the pledged scenarios are actually inadequate. Looking at some key technology components of electricity grids here. So you have the generation, so thermal, hydropower, solar PV, wind, and distributed wind and solar, going through transformers, inverters, and so on, and transmission, which is going to be a big thing. So high voltage substation, and then eventually feeding the grid from generation and trying to meet the demand. We have talked about grid designs elsewhere, but high voltage AC and high voltage DC transmissions are both going to play into this. You have probably read elsewhere, or you can look up my other podcasts in terms of the differences between generation, ease of generation for AC and DC versus transmission problems, or advantages and disadvantages, pros and cons of AC versus DC. Power grids comprise transmission and distribution networks with overhead, underground, and subsea AC and DC cables, each with different technology and materials. Of course, we have also discussed space-based solar and wireless transmission of energy. So we don't know how this will play out in terms of what game changer may come along. Key technology components of electricity grids. I repeated it for whatever reason. Sorry about that. Global high voltage direct current transmission. I just wanted to show this, that we expect this to ramp up in terms of the various players in China, India, whether it's overhead, underground, or under the ocean, and so on. Okay, so this is subsea cable, underground, and overhead, and you can see that China overhead is the biggest contributor here, with India, Brazil, Africa, and so on adding as well. In other words, HVDC, high voltage direct current transmission, is expected to increase. The global length of HVDC lines has almost tripled since 2010. So here is the historic record to today, with additions of overhead lines in China, North America, and India, and offshore cables in Europe. And this is expected to continue in the IEA projections. Some other details: how hydrogen pipeline network configuration could work. So you have sub-gathering and gathering here, supply side gathering and sub-gathering pipelines, trunk line, and with distribution along the way, sub-distribution, transportation, liquid hydrogen, for example. So large steel trunk lines are used to transport hydrogen at high pressures from production or import areas to demand centers. There are still a lot of technological challenges to be met here. Demand side distribution lines operate at medium pressure and connect large consumers or sub-distribution lines to the trunk line. Main message: as with natural gas, pipeline networks with large transmission trunk lines can efficiently transport large volumes of hydrogen over hundreds of kilometers. So this has to work out in terms of where it will be produced. So for example, Saudi Arabia wants to be a net exporter of hydrogen over time and has invested large amounts, so they want to shift away from depending on oil, which they see as something that will become less and less acceptable by the global community. So they want to move to hydrogen and be a supplier of hydrogen, for example. Technological pathways for long-distance transport for the supply of hydrogen and ammonia by tankers. I won't go into the details, but delivering hydrogen over long distances requires its conversion to a denser form through liquefaction or to a chemical carrier such as ammonia or LOHC. So conversion, transport and storage, reconversion, and use at the end Life cycle analysis and so on are needed to make sure that this still remains viable. CO2 flows through CO2 management value chain, so there is capture at various sources, transportation, and storage and use. Once captured, CO2 can be used on site or transported in most cases by pipeline or ship, either to a point of use or to a permanent underground storage site. Remember again, these are technological promises on which we are relying. This is the CO2 pipeline network, like H2 pipeline, gathering, subgathering, distribution, and then trunk lines transporting large aggregated volumes of CO2, typically in its dense phase. So efficient pipeline networks usually have a trunk-style transmission line with branches for gathering and distribution. Again, these are future visions, optimistic visions in terms of relying on technological promises. So that's a very brief introduction, but the report is very nice, available online, and very detailed with lots of references in each chapter, so you should definitely follow up if you're interested in the details. Okay?